So what we're just going to look at now is where that rule comes from. Okay, so this is for interest only, but we're going to look at where the rule comes from and how we find the gradient function. So if we wanted to find an approximate value of the gradient of the curve y equals x squared at x equals 5, so at this point here, okay, what we can do is we can pick a point slightly to the right. So let's pick the point at x equals 6 and draw a line between those 2 points. So what we've created here is a chord between the points x equals 5 and x equals 6, and we're going to find the gradient of that chord. So because this is the y equals x squared curve, when x equals 5, y is x squared, which is 25, and when x equals 6, y is x squared, which is 36. So if we draw in the triangle and work out the vertical height, so the difference between the y coordinates, which is 11, and the horizontal distance on our triangle, which is the difference between 5 and 6, which is 1. So the gradient is the vertical height, the change in y, over the change in x, so my gradient is 11. So we've got an approximate value for the gradient at x equals 5. Now we know that the actual value of the gradient at x equals 5 we could work out using that gradient function. So we said the gradient function for the x squared curve is 2x. So at x equals 5, gradient function, so at x equals 5 we know the gradient is 2 times 5, which is 10. Okay, so we've got an approximation of 11. So it's close, but it's not great. So if we picked that second point closer and closer to 5, we're going to get a better approximation of the gradient at x equals 5. So here we picked our second point at x equals 6. In this little diagram, we're going to pick our second point at x equals 5.01, so very, very close to 5. If we get the y coordinate at x equals 5.01, so we square 5.01, this gives us our y coordinate, 25.1001, and then from the x and y coordinates we can work out the vertical height of our triangle and horizontal height of our triangle. And if we then use those points to work out our gradient, we've got the vertical height, so 0.1001 over the horizontal distance, which is 0.01, and if we pop those into the calculator, we get a gradient of 10.01. So that's actually very close to what we know is the true gradient x equals 5, which is a gradient of 10. So the smaller we make that gap between 5 and the point to the right, the better our approximation for the gradient is going to be. So to find the gradient function in general, so in terms of x, we're going to use the same method as we've just used, okay? But instead of having the points 5 and 5.01, we're going to keep the x, and we're going to say that very, very small distance to the right, instead of being 0.1, we're going to call that h. So I've got my point x squared on my y equals x squared curve, still talking about the y equals x squared curve. And then the x coordinate that I'm picking slightly to the right, we're going to say it's x plus h, where h is that very, very small distance. So the y coordinate at that point will be x plus h squared. So if we look at, well, what's the vertical height of my triangle now? Well, it's the difference between the two y coordinates, so that vertical height is going to be x plus h squared minus x squared. And the horizontal distance on my triangle, well, that's the difference between the x coordinates, so that's going to be just my h. So to find the gradient, let's do the vertical distance on my triangle divided by the horizontal distance. Now if we expand and simplify on the numerator, denominator still h, let's simplify, so the x squareds cancel out, so we get 2xh plus h squared divided by h. So if we just factorise out an h on that numerator, we can see that those h's will cancel and we're just left with 2x plus h. So that's a general expression for my gradient function at the point between the points x and x plus h. So as the point to the right that I've picked gets closer and closer and closer and closer to my x squared, so as this h gets smaller and smaller and smaller, let's look at what's going to happen to the gradient function. So we can say as h gets smaller and smaller and smaller, or tends to 0, that means the gradient is going to get closer and closer and closer to 2x, which is what we know the gradient function for the x squared curve is. So this is just showing you, and it's called finding the gradient function from first principles. From first principles, how do we get that the gradient function of the x squared curve is 2x? So that's how we do it. I'm just going to show you now some sort of formal A-level notation for this finding the gradient function from first principles. Don't worry if it looks a bit scary, I'm just showing it to you so that you've seen it before if you're introduced to it at A-level, if you're doing A-level. So you'll see here I've got exactly the same diagram, and if you ignore this lim h tends to 0, what I've got algebraically there is exactly the same as I had on the previous slide. Okay, the only difference is we've got this lim h tends to 0 notation. So all that means is I'm finding what the following expression is as h tends to 0, as h gets closer and closer towards 0. Okay, so by the time I've simplified my expression down to the 2x plus h, I can then say, well, what is that expression going to be when h goes to 0? It's going to be 2x. Okay, so that's just the formal notation for the previous finding the gradient function from first principles. So in the red box here, we have got kind of the formula, I suppose, for any curve for finding the gradient function from first principles. Again, don't worry if this looks scary, it's just so that you have seen it. All right, we'll talk in a bit more in a minute about our notation for the gradient function, but this f-x and dy by dx are both different types of notation for saying the gradient function. Here we've got our limit as h tends to 0, and instead of the x squared curve, I've just got any general curve f of x. So this is my x coordinate, sorry, my y coordinate on my general curve f of x, and this is that point just further along where I've added that h. Okay, so if you do A-level maths, okay, you will use this general formula for deriving the gradient function from first principles, but for now it's just for interest. Just a little bit more, I'm just going to sort of do a little bit more notation just to try and explain to you where this sort of funny notation dy, so it says dy over dx, we call it dy by dx, comes from, because we will be using that quite a lot. So just again for interest to see where it comes from. In slightly more advanced notation, instead of using an h for the horizontal distance, that small distance we're moving away from x, we use this notation delta x. Okay, so a funny Greek d, delta x. And then that corresponding small change in y is called delta y. So using the delta x and delta y, our gradient function, again, this is notation, I'll talk to you about that later, for gradient function. So our gradient function is the limit, so instead of h tending to 0, we've got that delta x tending to 0 of the vertical distance on my triangle, which is delta y, over the horizontal distance on my triangle is delta x. And that delta y distance is the difference between the y coordinates, which we can see is the x plus delta x substituted into my equation of my curve, my function, minus the x coordinate of the point that I started at, which would be f of x. So When we're using this delta y by delta x notation instead of the h, the gradient of our chord is delta y by delta x, or delta y over delta x. The gradient at the specific point is the gradient of the tangent at that point. So my estimate for the gradient of the point, remember, is the gradient of the chord, where I've moved along a very small distance from my x-coordinate. The gradient at the point is the gradient of the tangent at that point, and we get to the gradient of that tangent as we make delta y and delta x much, much, much smaller. So it's the limit as delta x tends to 0, and instead of writing the limit as delta x tends to 0 of delta y over delta x, that is just written as dy over dx, which we say dy by dx. Again, really don't worry too much about where this notation comes from, that's just for interest, but when we're working out the gradient function, one of the forms of notation we will use for that is dy by dx. Okay, so let's just try and sort of do a bit of a summary of the notation and the different worded expressions you could hear for finding the gradient function. So dy by dx is called the gradient function. Because, as we saw at the beginning of the video, the gradient is the rate of change of y with respect to x, if you're asked to find the rate of change of y with respect to x, it means find the gradient function, find dy by dx. Sometimes it's called the derivative of y with respect to x, or sometimes it's called differentiated calculus. So, if we have the curve defined as y equals, and we want to find the gradient function, we would write that notation for the gradient function as dy by dx. So for example, if my curve was given as y equals x squared, I would say the gradient function dy by dx equals 2x. So instead of writing out in words gradient function, we're just going to write dy by dx. If, however, the equation of my curve is given in function notation, so if I was told f of x equals x squared, and we know that we can sort of interchange between y equals f of x, then the kind of matching gradient function notation, so we don't use dy by dx anymore, we use this f with a dash x, f dash x. And so it's just two different types of notation for the gradient function that go with the two different types of notation for the equation of a curve. We can also, and we sometimes see this, but if we would just find the gradient function for 2x to the 4, or differentiate 2x to the 4 with respect to x, we could see it written like this. So d 2x to the 4 by dx, and then we could differentiate it, so bring down the power, multiply it by the 2, reduce the power by 1, 8x cubed. We won't really see that so much with the Further Maths GCSE, but that is used sometimes at A-level. And the final thing just to note is, let's say we haven't got the letters x and y, let's say we've got the letters s and t, let's say it was a speed time graph, so instead of y against x we had s against t, then you obviously wouldn't use dy by dx for your gradient function, you would use ds by dt. So just different sorts of notation for writing down gradient function without having to write the words. So differentiation is the word that we give to finding the gradient function. If you're asked to find the gradient function or the rate of change of y with respect to x, we say that we differentiate the equation of our curve.